Welcome to the problem of the week for week 7, the divergence theorem. It's entitled Volume equals Area when using divergence. We're going to be looking at one of the problems from the laboratory that we did where we examined the divergence theorem and we examined Stokes' theorem for a couple of different examples. We're going to be looking at the first example, which was the divergence theorem, where we looked at integrals over the surface of the sphere and also over the volume of the sphere. So let's first examine the vector field that we're going to be working with. It is f is x cubed times the unit vector in the x direction plus y cubed times the unit vector in the y direction plus z cubed times the unit vector in the k direction. And using the fact that I can extract a r cubed times some angles, I will pull out the factor x squared plus y squared plus z squared raised to the 3/2 power. That's r cubed times the relevant factors, which are sine cubed theta cos cubed phi times I hat plus sine cubed theta sine cubed phi times j hat plus cos cubed theta times k hat. Now you might naively think this thing is somehow proportional to r hat, because it kind of looks like it's pointing outward from the sphere. But if we recall what the unit vectors are, and ER is given by sine theta cos phi I hat plus sine theta sine phi j hat plus cos theta k hat, and E theta is cos theta cos phi I hat plus cos theta sine phi j hat minus sine theta k hat, and E phi is minus sine phi I hat plus cos phi j hat, and you actually take the dot product of these things, you very quickly realize that none of them are zero. F dot ER is not 0, F dot E theta is not 0, and F dot E phi is not 0. That means F has components actually in all of these different directions, in the E theta, the E phi, and the ER directions. And so this might not be true perhaps at some special angles, but in most cases the field doesn't point just in the radial direction. So you just have to be careful with your intuition when you look at a vector field to try and determine exactly what direction it points in. Now, because we're going to be looking at the divergence theorem, we're also going to need the divergence of this vector field. And even though we can extract the radial, the theta, and the phi coordinates of this vector field, it turns out to be much, much easier to do this calculation in Cartesian coordinates. And so if I take del dot f, I'm going to get the derivative of x cubed with respect to x plus the derivative of y cubed with respect to y plus the derivative of z cubed with respect to z. And that will give me 3x squared plus 3y squared plus 3z squared. And when I put that all together, I'll get 3r squared as the divergence. And then the final thing we want to note is we're going to need to know what the unit vector is in the normal direction when we integrate over the area of the sphere, and that unit normal is of course just the radial vector E hat r. So we learn that n hat is equal to E hat r. Okay, we've got some integrals to do. Let's start with the surface integral. The sphere is going to have a radius of big R that we're going to use, and we're going to integrate over the surface area. And so the integral of the area ds of f dot n is just r squared. That r squared is coming from the integration measure, but because the r is constant, I can replace it by its radius. We have the integral minus 1 to 1 d cos theta, the integral from 0 to 2 pi of d phi. And then what we have is the dot product of the f vector with n hat. Well, I'm going to write n hat as xi hat plus y j hat plus z k hat divided by r. And so when I take the dot product, I'm going to just get x to the fourth plus y to the fourth plus z to the fourth divided by r. You can see now I can replace the x by r sine theta cos phi. I can replace the y by r sine theta sine phi. And I can replace the z by r cos theta. And I'm going to get a net factor of r cubed coming from that integrand, which when I add it with the r squared will give me r to the fifth. And I'm going to have a bunch of different angle terms. So I get this r to the fifth. I still have the same integral, d cos theta, d phi. And you can pretty quickly recognize that it's going to be sine to the fourth theta, cos to the fourth phi, plus sine to the fourth theta, sine to the fourth phi, plus cos to the fourth theta. Now, we need to do some integrals. We're going to first integrate over phi, but we're going to use this fact that the integral from 0 to 2 pi of cos to the fourth phi is equal to the integral from 0 to 2 pi of sine to the fourth phi. and they're both equal to 3 pi over 4, and that's going to allow us to integrate over phi. There's also an integral of just a constant, and that's going to just give me a factor of 2 pi. So after I do the integral over phi, I still have this integral d cos theta. I'll have a sine to the fourth theta times 3 pi over 4, plus a sine to the fourth theta times 3 pi over 4, plus a cos to the fourth theta times 2 pi. Now, I'm almost ready to do the second integral. I have to replace the sines by cosines, otherwise I can't do the integral. And so if we write sine to the fourth theta is 1 minus cosine squared theta quantity squared, and then I can expand that out, 1 minus 2 cosine squared theta plus cos to the fourth theta. Now that's a function of cos theta and allows us to do our last integral, which is a d cos theta. And so when we put all that together, the one term is going to give me 2 when I integrate it d cos theta. The 2 cos squared theta is going to give me a factor of 2 times 2/3 or 4/3. And the cos to the fourth theta term is going to give me a factor of 2 over 5. And then the cos to the fourth theta term is going to give me a factor of 2 over 5 as well. So I get this complicated mess, but I just take a deep breath and work out the arithmetic, and I find it's equal to 12/5 pi times r to the fifth. So please remember that number, 12/5 pi times r to the fifth, because we want to be comparing that with what we get when we do the volume integral. Okay, good. Surface integral is done. Let's now go on to the volume integral. So the volume integral that we have to integrate for the divergence theorem is the integral of the divergence over the volume. So I integrate over the volume dv of del dot f. Remember, we calculated what del dot f was. It was 3r squared. And so now I have a three-dimensional integral, so I'm going from 0 to big R dr, minus 1 to 1 d cos theta, and 0 to 2 pi d phi. I have the r squared from the integral measure, and then del dot f is 3r squared. Of course, this doesn't depend on any of the angular variables. The integrand is independent of that. So I can just immediately do the integral over the angles, and we know it's going to give us the solid angle, which is just 4 pi. And I can bring the 3 over as well. So I'm going to get a net of 4 pi times an integral from 0 to r dr of 3r to the fourth. I factor that 3 out, I get 12 pi. R to the fourth is easy to integrate. It's r to the fifth over 5. I evaluate it between big R and 0, and I get big R to the fifth over 5. And lo and behold, I get 12/5 pi r to the fifth. Now remember, I asked you to remember what the surface integral was. Indeed, it was 12/5 pi r to the fifth. And so we have shown now that these two integrals are actually the same. And so this is showing a verification of the divergence theorem. It doesn't prove the divergence theorem. It simply shows that for this explicit vector field, and for the case where we integrate over a sphere, we found the integral over the area of ds f dot n is equal to the integral over the volume of dv times the divergence of f. And I hope that you have been able to benefit by going carefully through this example and working out all of the different integrals. I'm also hoping that you are becoming more and more facile in working with these kinds of multidimensional integrals, in setting them up, making sure you understand exactly what the integration ranges are. So for example, in spherical coordinates, we always have a d cos theta, but if we were doing cylindrical coordinates, it would just be a d theta. So making sure that you don't make those kinds of mistakes and so forth. And that then concludes this problem of the week.